So the first thing I want to show you is Bruce discovered what seems to be a solution to the debugger connectivity problem. So I put an announcement about to this effect on Canvas. And since it's just a few steps, I thought I would just show you so that everyone can do this on their own machines. But within the MPLab environment, if you go to Tools, Options, select the embedded icon, and then beneath that icon, select the Generic Settings tab. This third checkbox down, Maintain Active Connection to Hardware tool, make sure that is checked. By default, it is unchecked. So if you haven't done this yet on your machine, you'll find that that's unchecked. If you go in and check this and click Apply and OK, so far, this seems to have solved our debugger connectivity problem. We experimented with this in lab yesterday, and after each of the groups did this, we didn't have any connectivity problems for the rest of the lab. So if nothing else, it helps. So please, the next time that you log on, go through that process and just set that up. And I think that's going to reduce our unplug and replug events a lot. I had a few observations from lab that I can go over in a moment, but Bruce, do you want to talk about ISR timing?
Just a couple of comments about ISR timing. Floating point is slow, and if you're using floating point in the interrupt service routine, you might want to know how many cycles the interrupt service routine is actually taking, because you only have a budget of about 909 before you run out of time. And the easiest way to time an interrupt service routine is to note that when the interrupt flag is set, timer 2 is reset to 0. So if you read timer 2 in the interrupt service routine, that will give you the total elapsed time so far in the interrupt service routine. If you put that if you read timer 2 at the end of your ISR, just before you exit, then that will give you the total execution time for the ISR, except for the number of cycles necessary for the context switch back to main, and which is about 50 cycles. So you can exactly get the number of cycles you are taking, and it has to be less than about 850 for this thing to work. There is a read timer 2 macro in plib. Read it into a variable and print the variable in a thread. Don't print it in the interrupt service routine.
So an interesting experiment to run is somewhere where you are either presently doing unnecessary floating point arithmetic, and I'll talk about a few of those places that might exist in your code, or somewhere that you're currently doing integer arithmetic. Replace integer or floating point with the other and measure the change in cycles that it takes for you to get through that interrupt service routine. And then you can actually quantify your optimizations, right? You can actually measure how many cycles you're saving by being careful about when you're applying floating point arithmetic and when you're applying integer arithmetic.
And that would make a great discussion piece in your lab write-up.
Certainly. You had a question, Raghav?
Yeah, I was wondering, how did we get to the 900 cycles number for the ISR?
So the 900 cycles number for the ISR comes from the fact that we are sending audio samples at 44 kilohertz. So we've decided on a 44 kilohertz audio rate. Our CPU is running at 40 megahertz. 40 megahertz divided by 44 kilohertz is about 909 cycles. So it takes you 909 CPU cycles to count up to the amount of time that elapses for one audio tick.
All right, thank you.
No problem. So along these lines, a few places, a few things that I've noticed in people's code in lab that I want to address, some sort of no-brainer places for optimization. The first is in your DDS calculation of the phase increment. We went over this in lecture last week. You'll recall that the process here is you use the quadratic or the sine function to compute your desired frequency in that audio sample as a function of time. So you're incrementing some variable in the interrupt service routine to keep track of how long have I been producing this sound. And you're using that elapsed time to compute your desired output frequency at that audio sample. And then to actually compute the phase increment for your DDS algorithm, you multiply that frequency by 2 to the 32 over FS, the audio sample rate, 44 kilohertz for us. As implemented, if you haven't changed anything in the code, this and this are both implemented as pound-defined variables, and they're both implemented as floating point variables, which means this division here is a floating point division. Do not do this division every time you loop through the audio interrupt service routine. Compute the quotient of these two offline using your calculator and put that number in to replace this division. And you will save yourself something like 130 CPU cycles every time through the interrupt service routine, which is a lot. If you think about it, so you have about 900 cycles to spend. If every cycle were a second, that's exactly 15 minutes. And by spending 120 to 140 cycles here, you're spending 2 of those 15 minutes every time through the interrupt service routine just computing this value, right? Which you could replace with a constant. So that's one source of optimization. The other one that I'm seeing is folks that are starting to work on the amplitude envelope calculation. They're making the correct observation that you can compute that ramp as a function of that variable that you're incrementing in the interrupt service routine to keep track of time, right? So I'm seeing a lot of code that is doing something like checking the value of that incrementing variable, and if it's less than some threshold, say 1,000, then it's doing a floating point division of the value of that variable by 1,000 to get a number between 0 and 1, 0 at value 0, 1 at sample 1,000, and multiplying it by the value that you're sending to the DAC, so that you end up with a linear ramp over the course of 1,000 cycles up to some maximum amplitude. I want to just point out that if a way that you could do this much more efficiently is you could consider doing something like say we have some counter variable that we're incrementing. So we would do some check if counter is less than 1024, then we would set this value that we're trying to scale, some value, equal to that value times counter shifted by 10. Is it clear what's going on here? So this counter is going to assume some value. As you count that up, it's going to go from 0 to 1023, right? So you're multiplying the value that you're trying to scale by some multiplicative factor between 0 and 1 by some number between 0 and 1023. A shift by 10 is the same as a divide by 2 to the 10, which is a divide by 1024. But by doing it this way, you're doing an integer multiplication and a shift, which is way faster than a floating point division. So this is another place where you could, by replacing one line of code with something slightly more optimal, you can save yourself quite a number of CPU cycles. Okay. And think about this as if this is becoming a problem. For many of you, you're getting through the interrupt service routine fast enough, and that's good. If you're starting to hear little jitters in the sound, it's likely because you're not meeting your deadline. And that's when you need to start thinking about some of these optimizations. The next lab, lab 2, is all about optimization. So we're going to spend a lot of effort in lecture and in lab really thinking about ways to save CPU cycles, okay? And then the other thing I just wanted to address, because we have quite a few groups that are finishing up lab 1 early, which is great. What should you do if you finish lab 1 early? You have a few options. So one thing that you should certainly do is start working on the lab report. And if you go to the policy page on the course website, you can find all the details for the lab report. Start working on that. And along those lines, one of the things that we ask that you include in the lab report is a spectrogram of the sound that you generate. You can do that in one of two ways. One way to do that is you can record the sound coming in through the microphone input to a WAV file, import that WAV file into MATLAB or Python or whatever you prefer, and compute a spectrogram. And in the lab write-up, there's an example of doing that in Python. So if you want to look at that, that's fine. The other option, the easier option really, is if you look at the day 0 lab write-up, there's a section that discusses using the sound card in the lab PC as an oscilloscope, using an application called waveforms. That will generate spectrograms for you automatically. So that's the fast way to do it. And if you want to do that, that's perfectly fine. We were working on doing that with a group yesterday. So just keep that in mind. The other thing that you can do is start working on Lab 2. Lab 2 is more involved than Lab 1, so you might thank yourself for having an extra week to work on it or an extra few days to work on it. Or the other thing that, if you have the time to do it, you could do. Does anyone know this expression, bump the lamp? Is this familiar to anyone? This comes from Disney animation. This is one of my favorite expressions in the world. But this comes from the movie Who Framed Roger Rabbit, which maybe many of you have seen, but it's a movie that combines live action actors with animated characters, including Roger Rabbit. And it was made in, I think, the early 80s. So it was before the era of computer generation, computer generated characters and such. So that animation of combining live actors with the animated characters was painstakingly done frame by frame by the animators. Bump the lamp is an expression that came out of Disney animation, where if you watch that movie, there's a scene where the main live action character and Roger Rabbit, who's the protagonist animated character, are handcuffed together and enter a basement. And the live action guy bumps his head on a swinging lamp so that the light is changing constantly. So they had to painstakingly map the changing light to Roger Rabbit in every frame of that scene. And you as the viewer don't even really notice it. They didn't have to bump the lamp, but they did. And so to bump the lamp is to do something difficult for the joy of it. So if you have the time in this lab, you might consider doing something difficult for the joy of doing something difficult. Maybe trying to synthesize a card or a Baltimore Oriole or some other bird, okay, if you want. But you don't have to do that. If you want to start working on Lab 2, that's perfectly fine. And what I want to do for the rest of the day is introduce Lab 2, simply because people are starting to wrap up Lab 1, which means they're starting Lab 2. So I think it's time to start introducing it. Are there any questions from anyone before I get into Lab 2? Okay. In that case, I'll remind you what we're doing in Lab 2. We're going to be doing the Boids lab. Is this video jumpy for you through Zoom? Or is it smooth? Okay, I hope it's smooth. But in any case, it's smooth in real life. So if it's jumpy in Zoom, that you can use your imagination to interpolate. In any case, we're implementing the Boids algorithm, which, as I mentioned in the first day of lecture, is an artificial life program. And it's an algorithm that generates shockingly realistic and organic looking simulations of bird flocks. And it does this by instantiating a whole bunch of individual birds, or boids as the algorithm calls them. And each of those boids follows a very simple set of rules. It looks in its local neighborhood and takes action, action being changing the direction and speed of its travel based on the direction and speed of travel that it observes in its nearest neighbors. And we're going to go over what those rules are, but it's a very simple set of rules. All of the members of the group follow these rules, and as a consequence, you get an emergent group phenomena that looks like bird flocking. And as you change the parameters that control this algorithm, you can change what looks like bird flocking to instead something that might look like fish schooling or locust swarming or something like this. And then if you change them too much, you can get behaviors that look completely inorganic. So it's a fun thing to play with, because as you play with these parameters, you'll find a certain combination of them where it clicks and your brain suddenly registers what you're seeing as organic looking. Suddenly it looks natural. And then you slide a little more and the illusion is lost. And part of one of the things that is strictly required for this illusion to work is smoothness of motion. So what this implies is that we are going to have a strict deadline associated with frame rate. Smoothness, you get smoother motion with higher frame rate. And experimenting with this a little bit, for me and for my brain, at around 30 frames per second, my brain is tripped. It looks organic and it looks natural. At something like 15 frames per second, it still kind of works, but some of the illusion is lost. So we're going to set the animation deadline for everyone at 30 frames per second. So that means between every frame update, you will compute the new positions of every boid in your flock, erase each boid, draw each at its new position, okay, and then wait for the next frame to update. At 30 frames per second, you have 33 1/3 milliseconds to spend. So as I mentioned, this is an optimization lab. So the challenge is, in 33 1/3 milliseconds, how big of a flock can you update? And this is going to be one of the metrics that we use to evaluate performance. So there's going to be some bare minimum number that's required. And then the challenge is, how much can you optimize? And like with everything, my recommendation is get it working and then optimize. Okay, but the challenge is going to be how much can you optimize? We're going to talk about a whole bunch of these techniques. But before I do that, I thought that I would just talk through the algorithm itself. And I'll mention too, what I mentioned this in the first day of class, but one of the fun things about a lab like this is it will affect the way that you observe the world. I love projects like that. For me, the birdsong lab did this too, where it affects the way that I listen to birds now, which is kind of nice and interesting. This will affect the way that you look at the natural world, and it will affect the way that you look at media as well. In the natural world, you will see behavior like this all the time now, because your brain's going to be tuned to it, and you'll notice it. In the media world, you'll see this sort of stuff in movies and in video games. As I mentioned, this was used in Tim Burton's original Batman. If any of you like video games, this was used in the video game Half-Life. And versions of algorithms like this with different sets of rules have been used in a lot of other movies. A big one being World War Z, the Brad Pitt zombie movie. You know, perhaps you've seen that. It's a good movie. You should watch it if you haven't. But the zombies in that movie are very fast and they swarm. They're all computer generated. And their behavior is an emergent phenomena based on a set of zombie rules. So it's a different set of rules than we're going to be implementing, but it's very similar in flavor. So you'll see it everywhere once you get comfortable with it. So let's look at the algorithm itself. And if anyone has questions, you can just interrupt me. So let's see. I'm just going to pull up the lab webpage. Boids. Okay. So there are 3 principal rules that we're following. Okay, well, actually, let me start by taking a step back. For each boid, for each member of your flock, you're going to be tracking 4 state variables. So there are 4 states that you update for each boid in each frame update. And that is the X and Y position of each boid and the X and Y velocity of each boid. So in a particular frame, you will draw each member of the flock at a particular XY position, and it will have a particular XY velocity. And then to do the next frame update, you will use its velocity to update its position and redraw it. And then you will run this algorithm to compute its next step position and velocity so that that changes with time. And by the way, the relevant units to use here are, for position, pixels, and for velocity, pixels per frame. Right? Those are the units that make sense for the problem that we're solving. You don't want to have to do unnecessary unit conversions, right? So it doesn't make sense to necessarily track boid velocity in meters per second, because when you go to draw to the TFT display, you're just going to end up having to convert to pixels per frame anyway. So keep track of velocity in pixels per frame and keep track of position in pixels. There was something else I wanted to say about this. I Can't recall. It'll come to me. So then how do you update the position and velocity of each Boid between frame updates? You do it by applying the algorithm that I'm about to describe. Essentially, each Boid is following 3 main rules and then a couple of smaller incidental rules that help with the illusion. The first is separation. So for each Boid in your flock, there are 2 relevant distances. One of those distances we call the protected range for that Boid, and it's closer to the Boid than the other relevant distance, which is the visual range. And these names are supposed to suggest what these distances represent. The protected range is basically that Boid's personal space that it wants to defend. You can think about this in nature as, a particular bird doesn't want another bird to be closer than some distance from it because it doesn't want mid-air collisions, right? So there's some personal space protected range that each Boid in the flock tries to protect. And then there's a farther visual range, which is how far each member of the flock can see. None of these have global knowledge, right? None of them know what any member of the flock is doing outside of its visual range. It can only see its local neighbors. That's a tunable parameter. Both of those are tunable parameters. And in the Python interface, you'll set these up as sliders so that you can change your flock's visual and protected ranges and see how the emergent behavior of the flock changes as you move these things. We'll do this, I'll demonstrate this in a moment, but that's what we're looking at here. So the first rule that each Boid follows is separation. It tries to protect its personal space. And it does that by following the following steps. So at the start of the update for a particular Boid, we're going to use 2 variables to keep track while we're updating the Boid of the positions of its neighbors, those that are within its protected range. And you can call these whatever you want. For this write-up, I've just called them close dx and close dy. So each Boid will look at every other Boid in the flock and determine whether that Boid is within its protected range. And if it is, so if it's not, it just goes to the next Boid, right? It does nothing. If it is within its protected range, then what it will do is increment each of these variables by the difference between its own x position and the x position of that other Boid, and its own y position and the y position of that other Boid. Once that Boid that you're updating has gone through every other Boid in the flock and incremented these variables as necessary, it then changes its own velocity by the value of these variables times some tunable factor. And this tunable factor is, we're essentially doing a weighted average of a bunch of different contributors to velocity changes. One of them being protecting your personal space, the others being what we're about to describe. And these factors here allow for you to change the relative importance of each of these. Does a Boid care more about aligning with its direction of travel with neighbors than it does with protecting its personal space? Or do you want these things balanced? You can play with that, and you're going to set up the interface such that you can play with all that stuff in real time. But visually, it kind of looks like this. If you have some Boid that you're updating, it has its protected range, it has its visual range. It tries to get away from the Boids that are red. It can see the Boids that are green, and these Boids that are gray might as well not even exist to this one because it can't see them. They don't affect its motion. Does that make sense? So we can look at this in the flock. So we have this flock that's set to some parameters. Right now, its protected range is 4. This is in units of pixels. If we increase the protected range of each of these Boids, the expected behavior is that they will spread apart. They're each protecting their person a farther distance from them. So let's increase this up to, say, 40. You can see the flock is now much more distributed, right? Each is protecting. And it kind of loses some of the illusion, right? It becomes something else that's not birds, but something changes. And the other thing that we can change here is the avoid factor, which is that multiplicative factor. We can make it not really care at all about protecting its personal space, and they'll tend to start to aggregate more again. Or we can make it care a lot about protecting its personal space, and they will maintain their distance from one another. I'm going to put these back to something normal. As we slide the protected range back down to a lower number, you'll slowly see the flock aggregate into clumps again. Okay, so that's the effect that these parameters are having on the flock. The next rule that each of these follows is alignment, which visually what's going on here is each boid that you're updating is ignoring the boids in its protected range, because all it wants to do is move away from those. But then it's looking at the ones that are within its visual range, but farther away from its protected range. And it's looking at the direction that they're traveling and attempting to point itself in the average direction that those are traveling. Because it wants to stay with the group, right? So it wants to fly with its local neighbors. So the way that it does this algorithmically is we zero a few variables here, x velocity average, y velocity average, and neighboring boids, which we'll use to keep track of the number of boids that are within our visual range. And then as before, for each boid, we loop through every other boid and determine whether that boid is farther than the protected range from us and closer from the visual range. So we calculate the distance to each boid and we see if it's within this region. If it is, we increment these two variables, x velocity average and y velocity average, by that boid's x and y velocities, and we increment the number of neighboring boids by 1. Once we've looped through everything, we divide these by the number of neighboring boids. We're computing the average velocity of the boids that are within our visual range and outside of our protected range. And then we gently turn our boid that we're updating in that direction. And we do so by subtracting our present x and y velocity from the average velocities of our neighbors and multiplying by this matching factor, which, like the avoid factor, is the tunable parameter that is the weight for this contribution to our velocity update. So we can see the effect that these have on our boids. If we increase the visual range, does anyone have an intuition for what the effect of that is? Each boid can see farther. What you're going to see less of is, as tuned right now, this flock, like a natural flock, will sort of chaotically split into groups and then coalesce and then split into more groups and then coalesce. If we increase the visual range, the expectation is that over time, that stays as one clump, because no boid is really leaving the visual range of other boids. So as you can see, our flock has aggregated into a single clump, and it won't separate from itself, only at corners, and then it comes back together. So that's the effect of increasing the visual range. We drop this back down to wherever it was. Once we drop it down, this will start to again split and then coalesce. And if we change the matching factor, so this is how important to the boid's velocity update is attempting to match the velocity of the neighbors. If we make this really high, the effect is that we lose almost all of the organic illusion. So I'm going to make this really high. And what you can see is every member of the flock is now moving in exactly the same direction and speed. It doesn't look real anymore, right? If you set this to, and by the way, I have this set up as reciprocal, so it's 1 over that. So a high number is a small value for the matching factor. If we make this essentially negligible, then what you can see is you lose all cohesion of the flock. No one's trying to match the velocity of the neighbors, so they're no longer moving as a group together. It's just a mess. So there's some sweet spot. I don't know, something like that. Okay, so that's the next rule that we're following. The third rule is cohesion, which is, in addition to attempting to match the direction of travel of its nearest neighbors, the flock wants to stay cohesive. Each bird wants to stay near its neighbors. So it will gently steer towards the center of mass of the group. So what it does is, very similarly to before, it looks at all of the green boids within its visual range. And instead of looking at their velocities, it looks at their positions, computes the center of mass of those positions, and then gently steers towards that center of mass. So each boid loops through every other boid. If the boid in question is within its visual range, it will increment these two accumulating variables that we're going to use to compute the average positions of the nearest neighbors by the other boid's position, x and y, and it increments the number of neighboring boids. It then computes the average by dividing each of these by the number of boids that contributed to that variable. And very similarly to the way that it updated its velocity with the matching factor, we steer its velocity towards the center of mass. So the effect of this is this centering factor here. If we make this very large, they tighten up into little chunks, right? They're all trying to fly towards the center of mass, and the groups become very sort of tight ball-like structures that don't have the organic. It loses some of the, maybe it looks a little bit like fish, actually. I think when you change this, it goes a little bit from looking like bird flocking to looking like fish schooling or something. You see sort of the tight bait balls. And if you don't center them at all, then again, the effect with that is a little bit less obvious, but you lose some of the cohesion of the group. Okay. You'll be able to play with this. This is 50, a 50 individual flock. Depending how you optimize, you might be able to get that up to something like 90 or even approaching 100. A couple other rules. This one's sort of obvious, but clearly we want for our birds to turn around at the edge of the screen. So the way that we do that is we decide on some margin from the screen where we want for the birds to start turning. And then once their X or Y position exceeds these margins, you increment their velocity by some small amount, some turn factor. The greater this turn factor is, the sharper the turn. And if you turn that up too high, it starts to look like billiard balls bouncing off of a wall, right? You don't want that. So there's some sweet spot where the turn radius looks right, and it just takes playing with it. I don't have that turn factor set as a parameter in the interface. You might want to do that. It might be something that's interesting to look at and to play with. So you certainly could. So they turn around at the edges of the screens. And then the last little rule that we have set up here is speed limits, which is just to say that an actual flock of birds, there's some lower limit to the speed that they can fly. Generally speaking, they can't hover. Hummingbirds can hover, but they also don't swarm. But if you're looking at like starlings or something like that, there's some lower limit to the speed. So we don't let them slow down beneath some minimum speed. And we also don't let them speed up past some maximum speed. They are allowed to change their speeds within some range. And in fact, giving them that degree of freedom improves the illusion, because some can catch up to others, which looks right. To your eye, that looks right. So you want to give them some room to play, but you don't want any stationary birds because it doesn't look right. And you don't want any that are just screaming across the screen at speeds that also don't look right. I'm saying look right a lot. This is a computer graphics problem. And in one of Bruce's old lectures, Bruce, you said something that stuck with me, which was in computer graphics, if it looks right, it is right. So you're trying to trick your own brain. So when you get this thing tuned, then when your brain says, oh, the illusion holds there, that looks organic, then it's right, whatever the parameters were. So you go through, these are the steps by which you update each boid's velocity. So the contributions to the velocity update include the velocity is updated according to getting away from birds in the protected range. So there's some change in the velocity associated with this. It's also updated in an attempt to align with nearest neighbors. It's also updated in an attempt to move towards center of mass. All of that is done between frame updates, and we haven't yet updated the position. Once we get to the end of updating the velocity, all of the contributions, right? So we get through the protected range one, and maybe the velocity vector goes boink and points down like this now. And then we also add the contribution to matching with neighbors, and that points it back up like this, perhaps a little bit. And then moving towards the center of mass perhaps moves it a little bit down. At the end of all those contributions, you end up with some updated velocity vector, and you use that velocity to update the bird's position. The new x position is the old x position plus the velocity. This works because of the units that we've chosen, right? Our velocity is in units of pixels per frame. Our position is in units of pixels. We're updating it in a time step of 1 frame. So this is an Euler integration essentially, but that delta t that typically appears in an Euler integrator is just 1 because we're using units of pixels per frame. Okay. So I have, for all of those parameters, I have some recommended initializations for each of those parameters to give your flock the right look to start, and then you can mess with it and in the way that we have been and see what the effect is. But just to help you debug, this set of parameters will give you behavior that will look correct to your eye. And because there's quite a bit of stuff here, I've provided some pseudocode here, which you can use to set up this whole update. So the pseudocode does, I've attempted to comment this clearly, but it's exactly what you would expect, where for every Boid, we zero all of those accumulating variables that are necessary for the protected range calculations and the matching calculations and the cohesion calculations. We zero all these things. And then for every Boid, we look at every other Boid. We compute the difference in its x position and our own x position between its y position and our own y position. And we determine whether both of those positions are less than our visual range. The reason to do this check is a little bit subtle, and it's because we're going to be using a fixed point data type with a range of something like 65,000 something. We're going to go over this in the next lecture. In any case, computing this squared distance involves squaring dx and adding the squared dy. If you don't do this check, you can overflow your variable, and your Boids are going to do weird stuff. So we do this check to make sure that when we do this computation, computing the squared distance, that we're not overflowing our data type. That's why we do this. And by the way, we're looking at squared distances here, not the square root of the squared distance. Why? Because square roots are slow. And why do them? We can just work with the squares, right? So we just work with the squared distances and do everything like that. We don't need to take the time to compute the square root of these things. So we compute the squared distance to Boids that are within our, that will not overflow our variable. If that distance is less than the protected range, then we increment those two variables that we use to keep track of the positions of birds that are too close to us. Otherwise, if it's not less than our protected range, but it is less than our visual range, we increment our variables that we're going to use to compute the average positions and velocities of our nearest neighbors by the position and velocity of that particular bird. And we increment the number of neighboring birds by 1. And then in the event that we have any neighboring birds at all, we compute these averages. These are divisions here, right? So we're not going to do this in floating point. It'd be really slow. These are going to be fixed point divisions. And then we update our velocity. We check whether we have to turn at the edges of screens. We check our speed and enforce some speed limits. And then once our velocity has been updated, we update our position. Okay. So this will all live likely in a thread for you, some sort of an animation thread. What's the complexity of this algorithm? It's a hard question. Is it n squared? So checking the distance from each Boid to each other Boid is n squared. But you don't have to run the whole algorithm for every pair of Boids. You only run the whole algorithm for Boids that are within a certain distance of one another. So it's actually kind of subtle. I don't know what the answer is. But checking the distances to all the other Boids is an n squared algorithm. But you don't run the full velocity update for every pair, only for a subset. And by the way, that's going to change with the configuration of your flock. Sometimes you'll have the Boids kind of in a clump, which means for each Boid, there are lots of neighboring Boids, which means you're running the algorithm more times and consuming more CPU cycles to update this frame than you might for the next frame when perhaps they're a little more spread out. And you don't have to run this algorithm as much. So you should be keeping track of the amount of time you have to spare between frame updates. And as the flock morphs around, you'll see that time to spare wiggle. It's not going to stay constant. Sometimes you'll have more time to spare, sometimes you'll have less time to spare, but you want to keep an eye on it and make sure it doesn't drop below 0. We'll look, if not today, then in a future lecture, we'll look at how to set up a thread at a fixed animation rate. I think we'll have time to look at that today. But through this whole thing, we're thinking about optimization, right? We have a fixed amount of time between frame updates. We want to run this algorithm as many times on as many members of that flock as we can. So you're going to be adopting the mindset of someone like a race car engineer who's obsessed with shaving weight, right? So you're gonna comb through and you're gonna look for any opportunity to save yourself some cycles. And any opportunity that you find, you're gonna save those cycles. And if you do that, you're gonna end up being able to animate more Boids. You end up with a lot of cycles. Often, there are a few no-brainer spots where you get a lot back. Not using floating point frees up a lot of CPU that's otherwise consumed doing floating point arithmetic. There are other places where you can get clever and detail-oriented and find ways to shave off a few cycles here and there, and it adds up. Just like in cars, right? If you buy the highest end McLaren, it doesn't even have door handles. It just has rope pulls because it saves fractions of a pound, right? So find yourself opportunities to save a few cycles here, a few cycles there. It's going to add up and you're going to be able to have a bigger flock. The other thing I wanted to mention up here at the top, I said that I couldn't think of something. It just came back to me. Here, keeping track of these states, right? I said that we're using units of pixels and pixels per frame. Clearly, when we draw to the TFT display, we cannot draw to a fractional pixel. So the pixel values that you draw are going to be 2 integer values. It's a 240 by 320 display. So your position is going to be somewhere between 0 and 240 and 0 and 320 in the 2 dimensions. In running this algorithm, however, it's important that you do the arithmetic with the ability to update the position by fractional amounts of pixel. This allows for a bird to move at slower than 1 pixel per frame, which is what you want. If you have a slow moving bird, you want to draw it to the same pixel a few frames in a row, and then you want to have it move to the next pixel at the correct frame. This is very, very similar to the direct digital synthesis algorithm, where we were keeping track of fractional amounts of index so that we could index into the correct spot in the sign table a few audio samples in a row, and then at the correct audio sample, move to the next index of the sign table. By keeping track of fractional amounts of pixel, we draw to the same spot a few frames in a row, and then at the right time, move to the next pixel so that our bird can move at the correct speed and in the correct trajectory. So we'll get into the data type that facilitates that. It's going to be a fixed point data type which you can either write the arithmetic for yourself. You can create your own fixed point data type and then write the multiply routine for that data type and use it as such. And we'll go over how to do that. It's not very difficult. Or this GCC compiler has some built-in fixed point data types that you can just use. And we'll go over those too. And that's probably the path of least resistance, but it's instructive to look at both. Okay. So here's the pseudocode. We're going to go over fixed point arithmetic next time. I want to talk just briefly about frame rate, because I said we're going to enforce a 30 frame per second frame rate. How do you do that in ProtoThreads? Here in this section of the lab write-up, there's a link to some pseudocode for a thread that has a fixed frame rate. And all that's going on here is at the beginning of the thread, when we first drop into the while one loop, we get the time, right? We do all of our thread stuff. And then when we ultimately yield the thread, we yield for a specific amount of time. And the amount of time for which we yield is the current time. We get the time again. We subtract the time that we gathered at the beginning of the thread. And we subtract from that the total number of milliseconds for which we want for the frame to last. So 67, this is set up for that's 67-ish
15
milliseconds. That's going to be a 15 frames per second frame rate. For you, this will be 33 to get a 30 frames per second frame rate. This makes sense. So you have 33 milliseconds to spend. You have consumed some of those milliseconds in this thread. So you subtract off the milliseconds that you've already consumed, and then you yield for the amount of time that remains. And the exercise is going to be to push this right up to the edge so that you have very, very little time to spare here. The questions about that? Okay.
What do you think happens if you ask the threader to delay for a negative time? Any guesses? It's not time travel.
I'm guessing since it's an unsigned integers, it will overflow in the negative side and it will be a really large value.
Exactly. Very good.
Which
So
will probably look to you like a frozen flock.
So it might be a good thing to check for a negative number, or at least report the number on the TFT.
And if it drops negative, yield for 0. And if it drops negative here and there for some configurations of the flock, your eye's not going to notice it, right? So you can get away with it a little bit. If your flock starts to stutter, right, then the illusion's lost. The question is, how big of a flock can you generate and maintain the illusion? Any questions from anyone?
Can we overclock the CPU a little, like go beyond 40 megahertz?
Sure. Yeah, you can try to do that. Like I said, the way to go do that is in that config file. You'll have to change the PLLs, and then be careful. Anywhere else in the code that assumes that CPU rate, you have to also adjust. So in the TFT header files, for example, I believe there are some places where a 40 megahertz clock rate is assumed. You'll have to go adjust there as well. You can do it. It would get you CPU cycles and a bigger clock, or in a bigger flock rather. My recommendation is to save that for one of your last optimizations. There are a lot of problems to solve in this lab, and the order in which you solve them is kind of important. So the first problem to solve is get some birds flying on the screen. Doesn't have to be efficient. Just get some birds flying on the screen, get the algorithm working, and then go through and start optimizing, adding birds little by little.
The other thing that will kill you with bumping the clock rate up to 60 is that the maximum rate of update of the TFT is 20 megahertz on the SPI line. And the SPI divider is set to 2 right now, which means that if you don't do anything, you will get 30 megahertz and the TFT will fail to initialize. So you have to divide by a factor of 4, which takes you down to 15 megahertz, which costs you 25% more time to actually write the TFT. Everything's a trade-off.
What's the record for number of boids?
This is the first year we've done this lab. So you guys are going to set the records. So one of the other places that you can optimize this is the demo that I showed you is calling a TFT draw circle routine, which if you go into the TFT header files and look at that function, it's an expensive one. So another place to optimize is instead of calling routines like that, make your own circle stamp and stamp down a circle instead of drawing routines like that. But by the most I was able to get was 90. And that was with, instead of drawing circles or shapes of any kind, each boid was an individual pixel, which might actually be hard to pick up on these webcams. I'm not sure. But with individual pixels, I was able to get up to 90. Many of you will likely beat me.
With an older version of this, in which it was billiard balls rather than boids, I was able to get about 140 by being fairly aggressive in optimization, but not too aggressive. And one student did 800 by converting the TFT write to direct memory access. That, my friend, is painful. But he had a lot of bandwidth. He did it for fun.
Other thoughts or questions?